Hi, my name is Agustin Biancardi, and today I'll be discussing one application for differential equations. And this is as part of my linear algebra and differential equations class that I'm taking with Professor Sabir Mali at Franklin and Marshall College. If you struggle with any of the topics that are being discussed throughout this presentation, I highly recommend you check out my professor's channel, which has a lot of free resources to help educate you on these topics. The specific application I'd like to discuss is that of modeling animal populations. This information is very important to those in the fishing industry, as fish farmers and fishing corporations all the time have to determine how many fish they like to harvest. This is highly influenced by environmental concerns, as overfishing could cause a lot of damage to an ecosystem. There are legal consequences for overfishing certain species, so they might want to limit exactly how many fish they harvest in a year. And there are also financial objectives, which are the most important concerns for us today in our model, as overfishing in 1 year could damage population growth in the future and thus reduce the amount of harvestable fish. So today we're going to be creating our model with MATLAB software, and it's going to help us optimize for the harvesting rates and the initial populations in a closed ecosystem. This will become clear as we progress through the presentation. Let's start working with an example. Suppose you're a fishing consultant and a fish farmer walks into your office because they'd like to start a farm on their pond. And they want to maximize the fishing harvest without depleting their fish stock in the long run. Suppose that y of t represents the number of fish at time t years, with the fish population growing logistically and governed by the following differential equation, which we will refer to as equation 1. And we also already know the following relationship between dy dt, that is the change of population, and y, the actual population. So on the y-axis of this graph, you have the rate of change, and on the x-axis, you have the actual population. So the first observation you might see is that once we start seeing a population of 200 fish, the rate of growth of the fish population drops to 0. And what this really means is that the fish population will achieve carrying capacity at 200 fish. The ecosystem simply cannot handle a population of, say, 500 fish because it doesn't have the adequate resources to do so. We also can see that the equation 1 represents a first order separable differential equation. In that rectangular box, you can see that we have on the left-hand side the standard form of the first order separable differential equation, and on the right-hand side we can see how I transform equation 1 to match that standard form. This is very important because now that we know what type of differential equation we're dealing with, it makes it easier to solve. We can actually solve first order separable differential equations by integrating both sides. As we integrate both sides, you might notice that the denominator of the left-hand side features a decimal point. I'm just going to multiply the numerator and denominator of the left-hand side by 100 to make things easier to work with. The 100 we see on the left-hand side, we can take it out of the integral, and we are still left with a nasty rational integral on the left-hand side. So we are going to actually, to allow us to use u substitution, we will factor out from the denominator y squared. On the right-hand side of the equation, we can simply integrate that as t plus c, where c is a constant. So here we can use u substitution. And an obvious candidate for u would be 200 over y minus 1. Here is how we transform our integral using u substitution. After actually solving the integral on the left-hand side, our objective should now be to start solving for y. So here we're going to multiply it by -2 on both sides. To finish solving, we will have e raised to both sides of the equation. And now we will use basic algebra to solve for y. So here we have our general solution, but we're not done yet because the general solution represents an infinite set of equations for the population of fish. And just to make it clear, if we were to have 0 fish to begin with, we wouldn't expect to see any fish population growth, right? It would just be a flat line at 0. But if we had a fish population starting at 100, we would be able to see some growth in the population as time progresses. And that is basically what we need to do when we start looking at a specific solution. We need to find the equation for each of these specific starting populations. And to do so, we need to solve for C at every initial population. On the top right hand, we have the general solution again in the box. Here we have 3 different cases for initial populations, just to demonstrate how this would work. So I'm going to go over the first one, but the other 2 follow very similar steps. So if y of 0 is equal to 50, that is when the time is 0 or no time has elapsed and the population starts at 50, we're going to get this equation right here. 50 is equal to that. And we need to solve for C. So as we go through the basic algebraic steps, we will arrive at this C value. And all we have to do is plug that into our general solution here, and that will give us our specific solution when the initial population is 50. Y is equal to 200 e to the 2t over 3 plus e to the 2t is the population of fish when the initial population is 50. And it will change over time, as you will see in the graph. In this graph, we can see 3 different functions. The one that we just calculated by hand, which represented the initial population of 50 in blue, the initial population of 100 in red, and the initial population of 200 in yellow. And we can see how these 3 different specific solutions compare. When the initial population is 200, the population remains flat, and there is no growth because it has achieved carrying capacity. But we can see that when it is 100 or 50, it doesn't matter. It will also achieve the carrying capacity. It'll just take longer. So the major takeaway from this is basically that as t approaches infinity, or in the long run, it wouldn't make sense to have an annual harvest of 200, or at least whatever the carrying capacity is, if the goal is to not deplete the population. Now, a very important thing I just mentioned is that we have no harvesting in our current model. And so we need to consider that, because however many fish we take out of the population could impact the ability of the population to grow and recover. So here we're going to update our model, and you'll notice that this is exactly the same differential equation that we had before, except we just changed the y into a p just to make it different. And this part right here is the only change. We're minusing by h. H here is a constant, and it represents the annual harvest of the year. So it's a very simple model to show a more realistic version of what will happen once we increase our activity on the pond. So let's start working with another hypothetical. The fish farmer has to choose between annual harvest of 70, 100, or 120 fish. And they must also choose between initial fish populations of 42, 101, and 150 fish. So what we're going to do is we're going to use MATLAB to graph these three different annual harvesting rates with each of these initial populations, and we're going to determine which of these combinations is optimal for the goals of our clients. Now remember, the goals of this fish farmer are to maximize the fish harvest without depleting the population in the long run. This is the bit of code that I wrote to create the slope fields and the graphs of the functions that I was just describing. And you're going to see that this bit of code here is going to create the slope fields, while this one is going to create the actual functions of the different population given those constraints that we were discussing previously. Here's what MATLAB came up with. We have 3 different graphs, and each featuring a different annual harvesting rate. On the left hand, we have an annual harvesting rate of 70 fish per year. On the middle, 100 fish per year, and on the right, 120 fish per year. Now, we can also see that there are 3 different functions in each graph. The orange one represents the population as with the initial population being 42. The yellow represents the population as with the initial population of 101. And the purple one represents the population when the initial population is 150 fish. So when we have to determine the optimal solution, it is oftentimes best to look at which are clearly not good solutions. We can identify that when the starting population is 42, regardless of what harvesting rate we're working with here, we will eventually deplete the population, which is not what our client wants. We also see that when the harvesting rate is 120, the other two solutions don't work either. The slope field indicates that for both the initial population of 150 and 101 fish to begin with, will also be depleted as time progresses. So these don't work. Now, if we look closely, the 4 remaining specific solutions do work. All of them are constant at worst and meet the demands of our client. He just cares that the fish population is self-sustaining. It could be self-sustaining at 1 fish. The only thing that matters is that the population doesn't get depleted. So if we're looking at optimal solutions, these two don't work because here we're producing 70 fish per year in figure 3 versus figure 4 featuring 100 fish per year. Obviously, we want our client to get the most amount of fish possible. So now, this is our optimal harvesting rates, but which of these two solutions works best? Well, obviously, we want to produce the cheapest outcome for our client as well. If we can achieve the same thing with an initial population of 101 fish as we can with 150 fish, it makes sense to give our client the cheapest option, which is this one. So to conclude, we would tell our clients that the optimal harvesting rate is 100 fish per year, and the optimal initial population would be 101 fish. In other words, he should purchase 101 fish for his farm. So hopefully our fish farming client had a very successful business thanks to our advice. And it just goes to show you that our models can be as simple or as complicated as we want them to be. In our case, we were operating under a very simple logistic growth model, but we could have also considered things such as temperature or the weather expected in a year, which also impacts the population growth of a fish species. We were also only trying to optimize for the amount of fish being harvested. We weren't looking at things such as profitability. And we had very simple constraint that we only were looking at, any solution that didn't result in the fish population eventually reaching 0. So all of these things being considered, our model was fairly simple. And I just wanted to show you just one way that we could have made it a little more complicated by creating a simple program that I'd like to share with you that optimizes for profitability. So before I begin going over my code, I wanted to provide extra context to what we're doing right now versus what we were doing in the past. So similarly to before, we are still going to be telling our clients how many fish he should harvest in a given year and how many fish he should purchase to start his farm. But this time we are not going to be told a selection of harvesting rates to choose from or an initial population to choose from. Before we were simply comparing between 3 choices of one and 3 choices of another. This time we have to come up with these on our own. Furthermore, before we were optimizing for the total amount of fish being harvested, and this time we will be actually maximizing profitability as our main goal. So the 2 biggest pieces of information that our client will be providing us are the carrying capacity of the farm he's trying to make and also the rate of growth of the fish species he's working with. On the left-hand side of this slide, you can find the different user inputs that we will be working with in our program. And if some of these aren't very clear to you, I will go over them in more detail as I actually execute the code. Now, on the right-hand side, you can find the general map for the program and what we want to accomplish. First step would be to create a growth model for the fish population. So previously, we were told how the population of a specific fish in a specific pond would change over time. But we might be working with a completely different type of fish and a different type of pond. That is because our fish farmer is going to be giving us his specific carrying capacity and the specific rate of growth for the fish he wants to farm. So we are going to actually create a different growth model using that information. And once we have a way to project the growth, we will see how harvesting and different initial populations affect it. And to do so, we are going to be testing between 100 and 1,000 different harvesting rates and initial populations. And we're going to see which of these combinations leads to the most profitable outcome for our client. So once we determine that and we compare all of them, we are going to return that suggestion along with other relevant information to our client, and hopefully he will use it to continue running a profitable fishing farm. Earlier I discussed how we really want to test as many values as we can for harvesting rates and initial populations, and that's what this block of code begins to do. It really just creates the sample that we'll be working with. And the way we do that I will explain very shortly, but first I just want to, for simplicity's sake, assume that the scale is 1 and the carrying capacity is just 100. And let's just go through the first loop. So we're passing through this loop here, and we arrived at h. So the first time we pass through the loop, h is going to be 100 divided by 1 times 100, which is 1, times 1. And then h will be equal to, the next time it passes through the loop, 2, 3, 4. Now, remember, this is a nested for loop, so we're going to be doing something very similar with the initial population. And let's just do IP, initial population. When we have an initial, when we have a harvesting rate of 1, we will also be testing out the initial populations of 1, 2, 3, 4, and so on till we reach 100 in this case. Now, that's basically what this block of code does. It's testing. It's not testing. It's creating the sample that we will be using for our testing. And you might notice that we have the variable scale, and the scale really is just something I put into the program because if we wanted to get a very precise amount for our estimates, we could increase the scale of the testing. So instead of testing 100 H values, we could be testing 1000 by having a scale of just 10. And I recommended that the user use a number between 1 to 10, but you could theoretically use 1000 if you wanted to. But after 10, the program starts to run very slowly, so I wouldn't recommend it. Now, you might be wondering, why are we using the carrying capacity to determine our sample? Well, I just used part of the analysis we had earlier. We said that the carrying capacity, once we reach it, it doesn't make sense to harvest the amount of the carrying capacity every year because in the long run, you're just going to deplete the population. So this is a constraint I created. We're not going to be testing values beyond the carrying capacity. And for the second reason, I mean, it doesn't make sense to purchase more fish than your carrying capacity because you would expect them to die very shortly. I also mentioned how, because this is a different kind of farm with a different fish species, we need to come up with our own differential equation to simulate population change over time. And that's what this will help us do. This is a formula I found from an open source Calculus 2 textbook from the University of British Columbia. And it shows that if we know the rate of growth of any population and the carrying capacity of the population, we can create a differential equation to model population change. And that is what we are going to be implementing in MATLAB in this line over here. And you'll notice that as we did earlier, we haven't incorporated harvesting yet, which is what we do with this minus h. And remember, we are testing the different h values and we're passing them on. So we're actually going to be testing, if we're working with a scale of 1, we're going to be testing 100 different h's and thus 100 different differential equations. And this is how we solve them. We use a function called OD45, which is a ordinary differential equation solver from MATLAB, which takes in a function, which we have right here, f, and a time interval. So I'm doing 0 to time. The time was established by the fish farmer. You know, maybe he wants to be working, testing for 10 different years. And we have the starting value, which is the initial population, which again, we are testing a lot of different initial populations. So that is how we basically start to determine, you know, what are the specific solutions given a harvesting rate and an initial population. If we look back at our plan for the program, we're actually very close to the finish line. We originally created a differential equation that accurately maps the specific pond and fish species that we were looking at. And we were able to select really a whole bunch of different harvesting rates and initial populations, and we have tested them. But in this testing, a lot has to happen. We need to have more information to gauge if one solution is optimal, at least compared to the previous one. And so that is what we're going to do here. We're just going to create more information that the program can run with. And that's why we have harvest, which is simply the amount of fish that we, at every iteration, expect to harvest and fish at that time. So if we have a harvesting rate of 70 fish per year and 2 years elapse, we would expect a harvest of 140 fish. Revenue is determined by whatever the fish farmer told us they expect to get from each fish, times that harvest that we just calculated. The cost is a little more complex. Here we have F cost, which represents the cost per fish, times whatever the initial population that the farmer wants to create. Now we have harvesting costs, which really just represents however many expenses the fish farmer expects per fish. So this is just to simulate if he has a lot of people being hired to fish for him, he might have to per fish pay a lot of people through that variable cost. And then we have a fixed cost, which is, perhaps he has to spend $100 a year to maintain the pond. And so that is just including that. Now, we can calculate profit by simply getting revenue minus cost. And this is what will be factored as we seek to optimize on the next slide. So hopefully I just showed you how we calculate the profitability at each iteration, as we're testing each possible solution. But how do we know if the solution we're dealing with is actually the best one? This is a very simple way we can do it. We can simply create a whole bunch of variables that represent really the optimal solutions, if you will. So for instance, we can have the optimal harvest rate, the optimal starting population, the optimal profit, and this is just for information, how many fish we expect to have when we're working with these different values. And the way we update these things is we go through this if statement. And if we ever see that as we're testing the profitability of a solution, that it's greater than the optimal profit that we determined earlier, we're going to update actually all of these values to reflect that, whatever it was during that iteration. So at the end of the program, there will only be one optimal solution, and we will display that, we will print it, and we will let the user know exactly how many fish he should purchase at the start of the simulation. How much profit can you expect from this, and how many fish should you actually be fishing every year? And on top of that, we will also let them know, this is how many fish you will harvest at the end of the simulation. And you're going to see that as we execute the code. So here we are in MATLAB. And of course, a lot of this should look very familiar since we basically discussed all the parts of the program. But I will be executing this code, and we'll just discuss what's happening as we go through. And after hitting run, we are prompted for the fish rate of growth. I'm just going to put 2. We're asked, what is the pond's carrying capacity? In this case, we could just say we're dealing with a population, a maximum population of 500 in this pond. How much does it cost to purchase a fish? We can just test out, $10 for every fish we're using at the start of the simulation. And what are the yearly fixed costs? So if we're maintaining the fish farm, every year we might have to dedicate a few dollars to maintenance. I'm just going to test out $20, which is not much. How much does it cost to harvest a fish? We could say that, if we have to pay somebody to do our fishing for us, we can just, we can have a variable cost depending on how many fish we're taking out. And one should do fine for our purposes today. How much revenue is earned for every fish? We can just put 10 as well. There probably wouldn't be that much of a discrepancy between the buy and sell price. How much capital do you have available? We can just pretend that our fish farmer has $600, $600 at the start of the simulation that he's willing to spend on this project. How many years would you like to optimize the harvest? So for the purposes of our estimation, we're going to consider the outcomes 10 years down the road. On a scale of 1 to 10, how precise do we want this, this estimation to be? I'm going to put 2 so that it runs fairly quickly. And you can see how it's calculating, and what it's actually doing is it's running everything inside this nested for loop. So it's solving the differential equations we create at every single harvesting rate, every single initial population in our sample. Then it's collecting all this information that really helps us determine the profitability of each solution we're testing. And here in the if statement, we're simply checking, is this the best possible solution for our purposes? And if so, what else can we know? What else does this tell us about what we have to do? How many fish should we be harvesting? What is the optimal amount of fish to purchase at the start of our project? And just for information, how many fish will we actually be harvesting by the end of the project? So once we have all that information and we've tested all the different solutions and we have our best one, we will display all that information we just collected, and it will tell our fish farmer exactly what he has to do. So in our cases, based on the user inputs that I had, the optimal starting population is 27.5 fish. It's not super realistic, but it's a model. The optimal annual harvest would be 12.5 fish per year. We will expect to fish a total of 125 animals, and we would anticipate a profit of $650. So of course, this might not seem like a lot, it's 10 years for $650, but if you were working with a larger pond and more capital to begin with, you might see a dramatically, different profit potential. My code should be available in the comments section or in the description of this video as a link. Of course, feel free to share any comments you may have or any questions you may have. I'm more than happy to respond. And thank you so much for listening to my presentation. I hope you found it informative, and have a wonderful day.